Yeah, if you check the announcement for the exam, I posted like the link to two videos that were like review videos that I did in the spring semester. It's essentially the same topics, so you can watch those if you want. Um, or you can just check them as you need because if you check the PDF, some of the problems on the PDF refers to those videos. Um, so yeah, you don't have to watch all the videos if you just get stuck. It's like basically the problems on the videos were problems from the PDF. So you can check on the PDF. I wrote which ones can be found solved on the videos, basically. So okay, but yeah, so I wasn't planning on doing a review in class tomorrow. Let me start with server one. Um, Here it is. Yeah, I'm just creating a new PDF for. Okay, so just give me a second. Although the stuff that we're about to do involving vectors, eigenvalues and eigenvectors is literally just about finding null spaces. So in a sense, it's still useful for the exam because like what we're going to do today and tomorrow is just finding a bunch of null spaces. So it's still like useful, like and finding determinants as well. So both things still are related to the exam. It's just but yeah, I won't ask about that per se. Okay, so the next topic in the course is this eigenvalue, eigenvector stuff. So that's like an important topic in linear algebra. Um, like eigenvalues and eigenvectors are like give you like a lot of like useful information about a matrix. So again, this will only be for square matrices, and you'll see why in a second. Although for most of the examples I'll focus on, they will be typically like they will typically be you know 2 by 2 and 3 by 3 matrices. So let me explain what the idea is. So imagine that you had like a matrix. So A is going to be a matrix. Since it's a square matrix, right? In fact, we can start with the 2 by 2 case if you want. You'll see it will be essentially the same. That won't matter too much. So you can start with the 2 by 2 matrix. So you can call A if you want A, B, C, D. Okay. And you can multiply the matrix by a vector. In this case, like the vector that you will multiply that by is like a vector with two entries, right? So you can do A times V, where V is like XY. Okay. And the more important thing that's going on here is like, because the matrix was a square matrix, or in this case, a 2 by 2 matrix, right? If the vector that you started with has two entries, then the new vector has two entries as well. So the initial vector, this one has two entries. And the new vector, right, has two entries as well. So what does that mean? Like, what does that allow you to happen, possibly? It's not that necessary, at this moment, it's not so clear whether this would happen in general or not. But what that means is that if you think about it more geometrically, what's happening here is that you have the XY plane, and you have the vector V, right? Like the vector is on the XY plane, okay? And when you multiply the vector by a matrix, right, remember that produces in general like the new vector. So in general, the new vector AB would just be somewhere else on the XY plane. So it would be somewhere else in here. So we can draw it like something like this. So like the situation that happens in general is that oops, like this. Let me put it here. So in general, what happens is that the vectors V and A times V are not on the same line. So typically, V and AV are two vectors on different lines, or are two vectors which are not parallel. But it maybe would it may happen by chance that for certain vectors like V and AV coincide, not necessarily coincide, but happen to be multiples of one another. But it could occur, and I'm about to give you like some examples so that you have like a better idea of what I mean. That in certain cases, V and AV are parallel. So where you would have something like this. And if that happens, if that occurs, that the vector and the A times V are parallel, you say that V is an eigenvector for the matrix A. So if this happens, what does it mean? So in this case, sorry, just give me a second. In this case, AV is a multiple of V. right? In this situation, like one is like since they're parallel, one is like a rescale version of the other. So we write that as A times V equals lambda times V, where V lambda. Okay, so what is here lambda? Lambda is just like a number, which you can think of as a rescaling factor. It's actually called an eigenvalue. This is called an eigenvalue for the matrix A. And V is called an eigenvector. So whenever you have an equation of this form, so what this equation is saying is like when you multiply the vector by the matrix, you just get that same vector possibly. No, that's not on the example. You just get when you multiply the vector by the matrix, you just get a rescale version of that vector. This is and this is called the eigenvalue eigenvector equation. Uh, well, it depends on what you mean. That it can be like it can have a row reduced to 0, 0, like just like a silly like just to write something very silly. But if you write like in a matrix just as 1, 0, 0, 1, like the identity, right? That cannot have like a row reduced to 0, 0, right? Um, is that making sense? In fact, you can only reduce it. You can only get like a rows of zeros in the 2 by 2 case if the matrix is not invertible, right? Well, it depends. I mean, a 2 by 2 matrix can be reduced. It just depends. You mean like a video of eigenvalues and eigenvectors, or just like a video, something like more like in general? Yeah, no, I think I know what they meant, but it's not. Yeah, I think I know what they meant, but it's not quite how you phrased it. But yeah, I'll once we get a little bit to how to find them, I'll explain what's going on. But yeah, I think I have an idea of what they were trying to say, but it's a slightly different thing. Um, so let me give you like let me give you oh, by the way, just as a remark, um, for these eigenvectors that we're going to find, the only interesting case is when in the eigenvectors, or this will not be the zero, has to be different from the zero vector, because for the zero vector, I mean, if you put the zero vector here, A times the zero vector is always the zero vector, so that's not interesting, right? So these eigenvectors must be different, are required to be different from the zero vector. Otherwise, it's not interesting because A times 0 is always 0, right? and this is not interesting. So when we're trying to find eigenvectors, we're trying to find vectors which are not zero, the zero vector. Otherwise, the problem would kind of collapse and it wouldn't be too exciting. So let me, before giving you the general method to finding these, let me give you an example, a more geometric example, just to help clarify the situation. So here's an example. Imagine I gave you this matrix. Okay, imagine that I had given you the matrix A. This is the matrix which takes well, let me write it down. Let's let's start here. Like imagine I had given you this matrix 2, 0, 0, -2. So what is this matrix doing? It's kind of useful to think about what the matrix is doing to a vector. So what's happening here? So what's going on here? So this matrix, right? It's taking a vector x, y. This is our vector x, y. So here you have this vector x, y. And the matrix, what it's going to do, right? What the matrix does, if you think about it, is that it's going to double the first entry, right? So here you had x, and here you had y. Now it's going to double the first entry, so you're going to get 2x here. But it's also going to double the second entry, but change its sign, right? So it's going to take it's going to, instead of like just doubling y, it's also reflecting it, right? Or changing its sign. So you, instead of having 2y, you have minus 2y. Okay. So the new vector, which is AV, is 2x minus 2y. So what this matrix is doing, right? What this matrix is doing is like doubling the vector, but at the same time reflecting it, right? Like it's like a mirror, a doubled mirror operation. We had seen before the mirror operation, right? This is kind of like looking, it takes it kind of is looking at the mirror, but also like doubling the reflection, right? So it's like this matrix A is kind of like takes the mirror of the vector, but that doubles its mirror image, right? Is that making sense? But so what if I give you this matrix, what does it mean to find so what does it mean to find like an eigenvalue and eigenvector for this matrix? What this means is that we're trying to find we are trying to find a matrix a vector that when you mirror it and double it, the new vector coincides it belongs to the same line as the original one. So let me see if I can show you this on GeoGebra so that you see how this looks like. It could be fun to do it like experimentally. Let's see. Yeah, let's do it this way because it will be fun. I think it would be nice to see it happen. Just give me a second. Okay. Yeah. So this would be nice to see. Okay. Yeah. I like this. Okay. So let me show you how this looks like on GeoGebra. Ha. Yeah. Let's show this on GeoGebra. So here is our this is the blue vector is a vector we start with, right? The red vector is a mirror image twice as big, right? So, oh, I do need this point. So I just will remove the label. So again, if I start moving it, you see like the red vector is always the mirror image twice as big. And in fact, you can also flip them around and the red vector continues to be, and this also works like, I mean, you can put the blue vector in any of the quadrants, right? But let's keep it on the first quadrant just to make it easier. So what I'm asking you is, can we find a blue vector, right, that will have the property that the red vector is just parallel to it? If you look at this, like all these vectors that I'm giving you, they are never parallel, right? So is there a way to find like a blue vector that happens to be parallel to the red one? What would you try to do? I don't know if anyone can think of a how can you try to make these vectors like look more and more parallel? That's like one way to say it. So for example, if you choose like the blue vector to be on the x-axis, literally, right? The red vector will be a multiple of that one, right? So will also be on the x-axis as well. So just to zoom in the situation, if the blue vector for almost every vector, the blue vector and the red vector do not belong to the same line. But if the blue vector happens to be on the x-axis, right, then the red vector would just be on the x-axis as well. So that means that if you take a, what that means is it's like saying that if you take a vector on the x-axis, that should be like an eigenvector of the matrix. And likewise, you'll see if you take a vector on the y-axis, right? If you take a vector on the y-axis, the red vector is just on the same line because it continues to be on the y-axis. So what that means is that also like a vector on the y-axis will be an eigenvector for it. So there are some eigenvectors for this matrix. It's that you just have to find, be a little bit careful when trying to find them. So let's try to do that on the iPad. So let me write that down what we just found. So my claim is that I'm about to give you like a way to find this more like uh, as a method, but what I'm trying to say is that if you take a vector on the x-axis, right? So if you just look geometrically, if you choose a vector on the x-axis, then the red vector happens to be on the x-axis as well. So that means that a vector, like what I'm trying to say is that a vector on the x-axis should be an eigenvector, and we'll show that this is true. So a vector on the x-axis should be an eigenvector of A. And if you take a vector on the y-axis, if you take a vector on the y-axis, the red vector is also on the y-axis. It's a little bit different because it has been reflected, so it actually points in the opposite direction. But that's okay because that's fine. The thing that matters is for them to be on the same line. So this is also so a vector on the y-axis should be an eigenvector as well. Okay. So how can we how can we maybe make sure of that? How can we check that with confidence? So this is like how we can find eigenvalues and eigenvectors in general. So how can we find it's very easy actually. If you remember like the equation for eigenvalue, eigenvector is this one. Okay. It's actually more convenient to write that down all on the same side of the equation. So this is the same as this equation. Okay. Which is the same as this equation. So this is the identity matrix. So basically what I'm doing now is like factorizing a v, because if you see like both terms have a v, so you can factorize it down. You can factorize a v. It's just that you have to be careful. Oops, there should be a lambda here. Sorry about that. And let me just put I for identity. So that's what this equation becomes like. It is maybe the thing that may be a little bit confusing is why am I putting like here the identity? That's just because you know, if you don't put the identity, it's kind of like subtracting a matrix from a number. You cannot do that. So for like the things for this to still have like sense in terms of sizes, you just have to put like the identity matrix, which you can always do because putting the identity matrix, putting the identity is kind of putting like a one when you're doing multiplication. That's how that makes sense. Okay, so why is that useful? Because why is this a useful way to say this? Because that means that V solves a homogeneous system. Okay, so that's why homogeneous systems are important. So V solves a homogeneous system. For the usually a homogeneous system has been for the matrix A. This is not a homogeneous system for the matrix A, but for the matrix A minus lambda I. Okay. Uh, but so far so good up to this point. So again, like finding an eigenvalue or eigenvector is the same as solving this homogeneous system. Okay, so these two things are the same. But so we want a solution to the homogeneous system, which is not the trivial solution. So remember, a homogeneous system has only two possibilities, right? It has either a unique solution. If it's a unique solution, it has to be v equals 0. That's the only, if there's like a unique solution, that's the only chance. Or it can have infinite solutions, right? So since we want V to not be the trivial solution, right? Because like I said at the beginning, that in the remark that we do not want the eigenvector to be the trivial vector. So we want this homogeneous system to have infinitely many solutions. So we want A minus lambda I E V equals 0 to be a homogeneous system infinitely many solutions. So that requires the determinant of that matrix to be 0. Because if the determinant is not 0, the matrix is invertible. And once the matrix is invertible, the homogeneous system only has a trivial solution. So this requires because otherwise the matrix would be invertible, and otherwise the matrix otherwise A minus lambda I is invertible, and hence there will be a unique solution. And that's all that you need to know. So that's how you'll find the eigenvalues and eigenvectors. So let me write that down more precisely. So here's like the method for finding eigenvalues and eigenvectors, and I'm about to show you that with these matrices. So the first step is to solve the equation determinant of A minus lambda I equals 0. Okay. You'll see how this looks in a moment. Solve this equation for lambda. Okay. So you'll see this is like an equation that we solve for lambda. These values that solve the equation are the eigenvalues of the matrix. These values are the eigenvalues of the matrix. And then for each eigenvalue, lambda that you found in part 1, that you found in 1, you solve A minus lambda I V equals 0. But that's essentially what is a homogeneous system? That's a null space, right? If you remember, that's why we talked about null spaces when 1 or 2 days ago. So that means that you must find, so we will find a basis for the null space. And these will be the eigenvectors. So it's only 2 steps. First is solving an equation involving a determinant. Once you solve that equation, then you find a null space. So it's always 2 things that you have to do. I'm about to show you how this looks like, but it's that's why we talked about determinants to some extent to do this, and also why we talked about null spaces to find eigenvectors. That's a reason for doing that. Okay, so let me give you a second to copy this. Okay, so let's do some examples. So let's do this for the matrix A that we were working with. So A was 2, 0, 0, -2. Oops. So in step one, you consider A minus lambda I. Okay, so A is 2, 0, 0 minus 2 minus lambda. I is 1, 0, 0, 1, right? That's the identity matrix. So A minus lambda I is 2 minus lambda, 0, 0 minus 2 minus lambda. Is that making sense? So that's what the matrix A minus lambda I looks like. And you find the determinant of that and set it equal to 0. So you need to take the determinant of this matrix and set it equal to 0. So you must solve this equation. But what's the determinant of this matrix? Well, this determinant is very simple. So it's just 2 minus lambda times minus 2 minus lambda equals 0. So when can this be 0? That can only happen when lambda equals 2 or lambda equals -2, right? So what that means is that there are two eigenvalues for this matrix, which are 2 and -2. Okay, so let me stop here first to check if there are any questions up to this point. So is that making sense how I solved the equation? So for each eigenvalue, then you have to find the eigenvectors associated to that eigenvalue. So that's like step 2. Which color did I use for step 2? Let's use 2 different colors for each eigenvalue. So 2. So now we have to find the eigenvectors associated to the eigenvalue lambda equals 2. And for that, you need to look at the null space. You need to look at the null space of A minus lambda I. So you need to look at the null space of A minus lambda I. But now lambda is 2, so you have to look at the null space of A minus 2I. So now we have to look at the null. What is A minus 2I? The matrix A minus 2I is the matrix 0, 0, 0, -4. And so here you have to remember how to solve a homogeneous system, right? Or like the null space. Remember that to solve the null space, you just have to find a homogeneous system. Usually these null spaces are very easy to find. And I think this is related to the stuff that you mentioned, this video that you were watching, that you would get like the rows of zeros. So this does happen when you're finding the eigenvectors in the 2x2 case. So if you want, I mean, not that it's necessary. You can swap the column and the rows. and then you can do minus row 2 over 4. So if you look at this, it just says that y equals 0, right? So the null space, so what does that mean? So that means that a vector on the null space inside the null space of a minus 2 lambda, sorry, a minus 2I must be of the form v equals, x comma 0, because y is 0, right? So that is saying that this vector has to be a multiple, right? So it is a vector that is on the x-axis, right? And it's a multiple of the vector 1, 0. So the eigenvector is any vector that's a multiple of the vector 1, 0. And in particular, that means that it must belong it must be on the x-axis. Oops. So is that making sense? So what I'm saying is that the first type of eigenvector that we're finding is an eigenvector aligned with the x-axis, which we kind of knew should happen because that's what I had drawn before in this picture, right? So this is kind of like case 1 of what we had here. If you have a vector on the x-axis, a times v will be twice that vector. So it's like so it belongs to the x-axis as well. Is that okay? And then there was another eigenvalue, right? There was a second eigenvalue. Let's see if I can put a different color for this one. So we also had the eigenvalue lambda equals minus 2. And for this eigenvalue, you have to look at the null space of a minus lambda I. But now this is the null space of a. Lambda is minus 2. So minus 2 becomes plus 2. So it's the null space of a plus 2I. But what is a plus 2I in this case? That matrix is 0, 0, sorry. It would be 4, 0, 0, 2, right? 4, 0, 0, 0, sorry. Because if you put lambda equals 2, if you put lambda equals 2 here, sorry, lambda equals minus 2. If you put lambda equals minus 2 here, you get 4, and this one gives you 0. So it's 4, 0, 0, 0. And how do you find the null space for that? Again, like for null space, you do the homogeneous system. So you can do row 1 over 4, and then you get 1, 0, 0, 0, 0, 0. And And so in terms of a system of equations, I just x equals 0. So that means that the eigenvector, so let me see how I wrote this here. So a vector v equals xy inside the null space a plus 2i must have the form right. So now I'm using this, which it means that it is a multiple of, so it is a multiple of the vector 0, 1. So it must be aligned with the y. Is that making sense? So the first type of eigenvectors were parallel to the x-axis. The second type of eigenvectors are parallel to the y-axis. Is that okay? Questions about this? I'm about to do another example. I still have time to do another one. So, but maybe before that, I just wasn't sure it was something else you wanted to. Okay, let's do another example. Let's try to find eigenvalues and eigenvectors for this matrix. Here's example 2. Just to make it simple, I'll put it up. So it's a slightly more complicated matrix, right? It's a little bit more complicated because the previous one only had zeros, non-zero entries on the diagonal. Outside the diagonal, everything was a 0. So this one is a slight modification where there's at least something non-zero here. Okay. And next, tomorrow I'll do like an example which is a little bit more complicated than that. Okay. But so again, for eigenvalues, so if you have this matrix, the eigenvalues are always found solving determinant of a minus lambda I equals 0. So what is a minus lambda I here? That's just 1, 3, 0, 1 minus lambda. The identity is 1, 0, 0, 1. So that gives you 1 minus lambda, 3, 0, 1 minus lambda. Okay? So the determinant of this matrix, right? So the determinant of a minus lambda I, in this case, what is that equal to? That's just 1 minus lambda squared. And that must be 0, right? So that forces lambda to be 1. So there's only one eigenvalue for this matrix, which is lambda equals 1. Oh, so that's good. So there's less work to do. Okay. So that's like the eigenvalue. And the eigenvector, right? How do you solve the eigenvector? you must consider the null space of A minus lambda I. But what is this null space? This is a null space of A minus I, in this case, or minus 1 times I. So it's the null space of which matrix? Well, just plug in lambda equals 1 here. So you get 0, 0, 0, 3. Okay, and how do you solve a null space? Again, you have to find a null space, you have to solve the homogeneous system. So you can put well, again, typically these homogeneous systems are very easy to solve. You can do root 2 over 3. So the system of equations just says that y equals 0. So any eigenvector, right? So the eigenvectors which belong to the null space actually take the form sorry, y is 0, so it's just x comma 0. So 0, so every eigenvector must be parallel to the x-axis in this case. But you'll see, so every eigenvector is parallel to the x-axis in this case. But now there was only one eigenvalue, so we don't have the case like last time where like we have some parallel to the x-axis and others parallel to the y-axis. And with the example that I'll do tomorrow, you'll see that they don't necessarily have to be parallel to either the x or the y-axis. It's just that these two examples were a little bit more simple. But tomorrow we'll do more examples where you'll see that the eigenvectors in general can be anywhere. Like they can be parallel to any line on the xy plane. Doesn't need to be necessarily the x or y axis, but it's better to start with something more simple. But yeah, so I think this is enough for today. So tomorrow, but as you see, like we're finding just a bunch of null spaces and determinants. So it's still like useful things to do. Practice for the exam. So tomorrow we'll continue finding eigenvalues and eigenvectors. I'll tell you some properties about them and what they're useful for. If that sounds good.